All right. Hey, so guys, there's a couple things we need to chat about this morning, but I think what we'll actually do is start by looking over homework. You may as well, obviously you need to get your homework packet out to do this, but in addition to that, you're going to have a bunch of time to work on your homework today. That's planned. We'll talk more in a minute, but you may as well get it out because you're going to turn to it in like 20, 30 minutes. So you may as well have it available right from the start. So I didn't get any angry emails from you guys, but I did from some of my other students. Some of these answers are completely wrong. I didn't know, but when they pointed them out to me, I was like, oh, that's embarrassing. And then frankly, I went back to change the answers and found that I had lost the original document that these PDFs are based on. So guys, I need to fix them, but I didn't have time, so we can just at least talk about it. I should be careful. I think all of the Lewis dot structures are okay. The mistakes that were there came later in the assignment. So guys, you know the drill. And actually, London, you and I talked, and I talked with all of you guys. We are going to continue to record homework assignments online. The reason is because between when I saw you on Monday and Wednesday, when I had time to talk with Ms. Call about it, I already have like 5 students that are in quarantine. I was hoping that a result of this new policy would be that we wouldn't have as many kids quarantined, but that's not proving to be the case. So guys, we are going to continue to record assignments online just for consistency's sake. So, guys, that said, turn this over to you. Please understand your drawing should look a little bit different than mine, simply because you should have drawn the polarity arrows in for the individual bonds. I only put the polarity arrows for the molecules simply because it cut down on clutter. So, McKay, go ahead. Mm-hmm. Yeah. Exactly. So if something is, the thinking is this, if something is symmetrical, all of the poles cancel out. And that's really what we're talking about here is it won't have an arrow. It'll have non-polar underneath it. And you're going to find out starting next time, these things are gases. So because they're not polar, they don't attract each other and they tend to be the gases. The ones that are polar tend to be liquids and even solids if the poles are strong enough. And we'll talk more. Yeah, exactly. Yeah, and that arrow represents the direction of polarity. Yeah. So, guys, questions on 1 through 4? Yeah. Yeah, that's a good question. So, and here's why. Like, for example, on number, so the question is, why did I draw the arrow off-centered a little bit? And the problem is a lot of times if you draw the arrow down the middle of the molecule, it hides things. So, wait, is that a single bond or a double bond with a line over it? You know that can't be a double bond because hydrogen can't double bond. But this one, But here what I found is if I moved this over, it hid those electrons. So I just pushed it out of the way just for clarity's sake. You should draw it straight down the middle. So guys, let me ask you this question. This was new relative to what you learned in class, and it goes like this. This bond goes this way, this bond goes this way, this bond goes this way. So guys, all 3 of these bonds are pulling opposite each other. So why is the overall arrow towards the oxygen? Did you pick up on that? Because you're going to need to know this today. Why is the overall arrow that way? Should we just talk about it? So guys, the idea is that oxygen is stronger than chlorine. So yeah, this is pulling this way and this is pulling this way, but this oxygen is pulling that way harder, and as a result, the overall drift is towards the oxygen. So it'll always be towards the strongest element regardless of the direction of those other arrows. So you guys good through 4? Okay. So any others of the Lewis dot structures you guys want to look at? I'm happy to go to any of them, but well, here we can sort of go through them page by page. So McKay, here's an example of one that's non-polar, balanced the whole way around. Any there? Guys, what about this? On number 7, I'm guessing for some of you, your arrow was not pointing up because you didn't put your chlorines in the same places. You understand that's okay, right? Like, for example, if you would put this chlorine down here, then the arrow would point in the other direction. So realize you don't have to draw them exactly like me. Your arrows just need to be oriented the same relative to where you put the elements. Other things on these guys? So let's go down here through number 10. Guys, I don't know what happened here. This is supposed to be a hydrogen. I think that, okay, that was the only one that got cut off there. You guys good there? So let me, yeah, please. Yeah. Oh, and 7, sorry, hold on. Let me go back. I was like, wait, 7. Go ahead. What? They are, but here's the difference. So chlorine's going this way, chlorine's going this way, this chlorine's going that way because chlorine's stronger than nitrogen. But the trick is this. This is a pair of electrons. It's not another chlorine atom, so there isn't a chlorine pulling in this direction. So it looks like so understand that white is hydrogen, right? But we'll count it. So say that the whites are chlorines. So the idea here is that this, let me orient it like this way. So the idea is this chlorine's pulling this way, this chlorine's pulling this way, this chlorine's pulling this way. So the overall pull is up because there isn't another chlorine down here pulling in the other direction. Is that okay? What else, y'all? Yeah, Sam.
For number 10.
Hold on. Yes.
I thought we were supposed to put the chlorines and the hydrogens like across.
Yeah, I'm so glad that you mentioned that. I would have forgot. And this is the idea. Guys, be careful on number 10 because there's the possibility that this one could trip you up. So guys, this is what, sorry about my mask, this is what number 10 looks like. And so the idea is that if you drew it like this with chlorines and hydrogens opposite each other, it looks symmetrical. The problem is it's actually not, and you can see it when you draw it like that. So guys, the take-home message is when you're drawing these Lewis dot structures, if there's a way that you can draw them so they're not symmetrical, organize them that way. And so I did it with the chlorines over there and then the polarity arrows that way. Sam, was that okay?
Yeah.
What else, you guys? Are we good on these? Okay, so let me go here, let me go here. I think we've, yeah, and this is the last of them. Again, the hydrogens got clipped a little bit, but there's not much I can do. What else, y'all? You okay? Right, you look like, is there something you're thinking?
No, I'm just...
Got it. Okay, you guys good? All right, so let me go on. Guys, this is where the mistake was in number 16. Did you guys find it too? The problem is, so let's talk. In number 16, what you're doing, and this is important that you understand this, because you're going to be doing it today. So what you're doing is you're calculating the polarities of these bonds. We're going to do this more in just a minute, so let's talk about it. So what you're doing is you're calculating the polarities of the bonds. We didn't talk about how to do this in class, but I wanted to introduce it to you by leading you through the question. So guys, what you had to do was look up the electronegativities of these elements and then subtract them. Remember, electronegativity is strength, so if you know the strength of this and if you know the strength of this, if you subtract, that gives you their difference in strength, which is then the polarity. The problem is that my numbers are wrong. When I did these like 5 years ago, I did it off another version of the periodic table, and since then they updated some of the values. And guys, that happens all the time. The numbers on this periodic table are shifting as we measure better and better. And so some of these are wrong, guys, simply because the numbers I used were different than your numbers. So don't mark number 16 wrong. Just understand the big idea, which is to find the polarity of a bond, subtract their electronegativities. That's all you got to do. So, other questions on any of this? The whole shooting match all the way down through number 20. You guys okay? You're sure? Okay. So guys, let's do this. Tuck your homework away. But no, well, that's not true. Just sort of shift it to the side. We're gonna be working on more homework in a minute. But guys, today you're gonna need note-taking materials. You're gonna need your periodic tables. Get settled. I would grab a pencil and not a pen because you're going to be erasing again. And then guys, we're gonna chat for a second and then we'll get going. By the way, guys, as you're getting settled, and I got to be really careful how I do this because I know that we live in a world that praises people for doing things they should be doing anyway. That's why we give trophies to everybody instead of just the winners. But, guys, thank you for being to class on time. I get the sense that some of you have made a commitment to do that this year, and believe me, it does not go unnoticed. Thank you for doing that, and let's keep it up. So guys, let me get rid of this and get rid of this and do this really quickly. And bless you. And yeah, we'll do this. All right. Get rid of this. So guys, before we get started, for those of you that aren't aware of this, most of you are sophomores. Well, most of you are juniors. A few of you are sophomores. If you're a senior, this doesn't apply to you. But guys, at the end of the month, if you're a junior, you're going to be applying for your classes. You're going to be registering for your senior classes. So we're looking about that last week in January doing the test group, and then the first week in February, this is going to open wide up and you'll be registering for your classes for your senior year. And so, guys, we can talk about this more over the coming days if you want, but I'd like to talk with you right now about this. AP Chemistry. I'd like to dispel some rumors. I'd like to talk with you about the opportunity that it provides. If you have questions right now, I'd love to answer them. And then if you have other questions you'd like to talk about personally, I'd love to talk. But guys, let me just tell you this right up front. I will never offer you advice about taking my class in order to protect my program. I don't care about my pass rates, although they're ridiculously high. Guys, I'm never going to go to you and say, hey, you should take AP Chemistry because I just want lots of kids in my class. I will always do what's best for you. But guys, with that said, I know that there are people in this room that will regret not taking AP next year if you don't do it. So what I'd like to do is I'd like to talk with you about who should be taking AP Chemistry next year. And guys, the answer is anybody that is getting into a science-related field as they move into college. That could be people that want to be engineers. Make sure you also take a lot of calculus as well and physics. But guys, if you're thinking engineering, if you're thinking obviously chemistry or biology, and we'll talk more about that later if you'd like. And then guys, certainly anybody that's thinking about the medical field, and that goes all the way from dental hygienist up to brain surgeon. Not that one is better than the other, but guys, if you're thinking medicine, it would be a big mistake. Even nursing, you name it, PA, whatever. Guys, you need to come and take AP Chem next year. So let's talk about why. Guys, the deal is this. Chemistry is the hardest class that you will take as a freshman in college. It is a bugger. They use it to weed people out of programs. So for some of you, passing the AP test would give you the opportunity to not have to take chemistry at all in college. For others of you, I will encourage you to take freshman chemistry and then knock the ball out of the park simply because you've already seen the material. And guys, I saw this firsthand. My son is moving towards medical school. He was a freshman at Utah State. And guys, repeatedly last semester, he would call or email me and go, Dad, thank you. I'm the only person in my lab. I'm the only person in my study group. I'm the only person in my class that knows what's going on, and it's because you taught me last year. And understand, guys, I'll just be honest with you. My son did not like AP chemistry. He took it from me. He came over from Temp. And my son's a biology guy. He liked biology a lot more than chemistry. He did great in the class, but it was not his passion. But guys, repeatedly last year, it was like, thank you, thank you, thank you. And guys, I get that all the time. I could show you a whole inbox full of emails from students that have said thank you. So with that said, let me tell you about the class. A2 is lecture. I don't know if you know this, it's a 2-period class. So guys, A2 is lecture. It feels like this, only it's a smaller group, and frankly, it's fascinating. We get to talk about some really cool stuff. But guys, A2 is lecture. Every day it's new material, it's homework, it's grading homework, it's taking tests. It's kind of what college chemistry feels like. But then this is the cool part. Guys, I'm the only teacher in Alpine School District that gets a second class period to teach a lab. And it's awesome because during A3, all we do is labs. There's no homework, there's no tests, you never take anything home. Guys, A3 is exactly what you thought a science class should look like. We are in lab every single day doing labs, writing them up. If you were to look into my lab right now, guys, there's a lab set up in there for my AP kids that's taking us 3 days to complete. We do these huge multi-day labs. It's really, really cool. So it's a wonderful deal. But guys, understand, you have to take second and third periods. You need to take them both. And I know that's a big ask in terms of your schedule. But guys, I promise you, you will not regret it if it's best for you. So I'll shut up in a second. But guys, if you want to talk about this, I promise you I will be honest with you. And if you sit down and go, hey, Mr. Knappenberger, this is what I'm thinking about down the road. Should I take your class? Guys, don't be offended if I tell you no, because I will be really honest with you in terms of what's best for you. I won't suck you into my program if it's not the best place for you. But guys, some of you in this class will be very, very thankful if you do it next year. So guys, with that said, any questions about AP stuff or science or any, have you guys even started to think about your schedules for next year? It's coming, y'all. I didn't know either. I went down and talked with Heather Red, our registrar, and she said last week of January for planning, and then first week of February, we're actually going to start scheduling. So, you guys good? We're all right? Okay. So, guys, seriously, if you ever want to talk about this, I will, and we do this a lot in the science department, because I'll have people that come to me and say, hey, should I take physics, chemistry, or biology? And I promise you, we'll figure it out and we'll do what's best for you. Because I think for a lot of you, AP Chem is going to be a great, solid choice. So as questions come up, please let me know. And yeah, it'll be great to have some of you back next year. So you guys good? Really? Okay. So guys, grab something you can take notes with. Grab something you can take notes on. Grab your periodic tables. And guys, we're going to dig into this. Today is going to begin with laying some foundation and getting some ideas out there. But guys, check this out. 4 slides of notes. That's it. Today's going to be really, really fast because there's a skill that you need to learn that then allows us to talk about the really interesting stuff next week. So guys, the date today appears to be, oh wait, I'm on the wrong watch screen, the 7th. And the topic for your notes today is on the board. So guys, today what we're going to do is we're going to talk about polarity and intermolecular forces. Again, it's a transitional day. And we'll make more sense of that in just a minute. All right, so guys, let me set the stage for you. So the homework that we just graded, and McKay did a really good job of bringing our attention to this as we were grading homework. Guys, remember in the homework that we just graded, those arrows mean something, and what they do is they tell us polarity. And McKay did a really good job of saying, okay, so let me get this straight in my head. If there's an arrow, it's polar. If there's no arrow, it's nonpolar, and you're absolutely right. Well, guys, what we're going to do today is we're going to start a two-step process. We're going to take this idea of polarity and link it to something called intermolecular forces. That'll be today. Then we're going to move past that when I see you again on Monday, and we're going to say, okay, if a molecule has intermolecular forces, how does it behave? And Monday is going to be all about the progression from there, which you guys you'll see this is very progressive stuff, but we're going to lay the foundation today. And guys, I would really, you be judicious, be careful in what you write down, but this is the idea leading you through the ideas. I don't think you need to write this down. But guys, last time in class, this is what we did. We learned that polar covalent bonds can lead to polar covalent molecules. And again, as McKay said, it's about symmetry. If a molecule is symmetrical, it's not polar. If a molecule is not symmetrical, it is polar. And guys, remember we represent these polarities with arrows. You guys are all good there, right? So you're not writing it down? Okay. So guys, this then is what we're going to do in the next 2 days. We are going to look at how these polar molecules behave when they get together in large groups. But guys, we're going to break this down into 2 days. We used to do this all in one big day, and it was a huge mistake. But what you're going to see in the homework packet is the next homework assignment says 2 and 3 in it, because we're going to separate it into 2 days. So guys, after this, we'll dig in and start talking about what you need to know. So guys, today what we're going to do is we're going to discuss how these molecules, we're going to discuss how to know which molecules are more polar. Last time in class, we figured out, is it polar or not? Today we're going to talk about more, which comes back to that idea of subtracting electronegativities. Then guys, the next time I see you, we're going to look at how these things behave differently, and that will be our day on Monday. Do you understand what we're doing? Then guys, start taking notes here. Intermolecular forces. The thing that's really interesting is that because of this pandemic, this class is all out of order and kind of ski-wampus, but so is my AP class. We're doing things in a different order. But guys, the thing that's been really weird is that in many instances, you guys and my AP students are doing the same stuff. We're talking about intermolecular forces in AP as well, which has never happened before. But guys, the thing that's interesting is this. Intermolecular forces are huge and fascinating, but I'll tell you right now, especially at the AP level, they can be a little confusing. So we're going to slow down. We're going to make sure that you understand the underlying ideas. We're going to build a good foundation. So guys, this is worth getting in your notes. This is actually the only page of notes that you're going to take today. Scratch this down. So guys, today the linking idea are these things called intermolecular forces. So guys, it's going to be worth writing down the subtitle there, intermolecular forces. So guys, the underlying idea is this. We talked last time in class, and it was even in homework, that water molecules are polar. I'll let you catch up and then we'll talk. You guys okay? All right, so this is the idea. Is a water molecule, just looking at what I got in my hand, is this symmetrical? No, certainly not. There isn't a hydrogen there. There isn't a hydrogen there. It's not symmetrical. So because it's not symmetrical, as McKay pointed out, it's polar. And we know that oxygen is stronger than hydrogen, so it's polar in this direction. Well, guys, check this just a second. Check. So here's what happens. When these polar water molecules get together, they don't link together like this. Why not? Why wouldn't they link together like that? Yeah, exactly. So, and we'll say it this way. The idea is this is the negative dipole, this is the negative dipole, and negatives don't attract, they repel. So what happens is they actually stick together, negative dipole to positive dipole, and when you get a whole bucket of these things, they all stick together and you end up with a beaker full of liquid water. And guys, that's why water is a liquid. It's because of these intermolecular, these polar molecules sticking together. So let's pull some of this water out. So this is like a drop of water. And so the idea is that they're all linked together, positive dipoles to negative dipoles. But guys, these linking forces, it just evaporated. These linking forces between these molecules are not bonds. They're weaker than bonds. The bonds are inside the molecule. These weaker forces that exist between the molecules, those are called intermolecular forces. Sam, go ahead.
This is just a question about the
Yeah. Yeah.
So, how come the oxygen in, say, the oxygen and chlorine, how does
Yeah.
the oxygen outpowers both of them?
That's a really, really good question. We didn't have Spirit Bowl last year, did we? No. Okay, so, but most of you have seen Spirit Bowl, right? Okay, the last time we did Spirit Bowl, did we do the massive tug of war where we get the rope that actually has 4 legs on it? Did we do that? Okay, then you don't know what I'm talking about. Let me draw it for you. So, guys, some years in Spirit Bowl, and by the way, I should mention, there's actually the chance we could do Spirit Bowl this year. I like that. So, guys, the idea was this. Some years in Spirit Bowl, we would actually rent a tug-of-war rope that wasn't a single-stranded rope. It was actually a rope that had been braided together so that it actually had four legs that all met in the middle. And we would do a tug-of-war, and we would have the sophomores, the juniors, the seniors, and then the faculty each grab a hold of a rope. Do you get the idea? And then whoever won, which was always the faculty because we have Bob Steele, we would, seriously, we just put Bob on the end of the rope and said, go that way, and we won every year. So, but guys, so to your question, it goes like this. Imagine that we didn't get a 4-legged rope. Imagine that we got a 3-legged rope. Do you see how that's connected to the molecule that Sam's talking about? So here's the idea. Say that this is Coach Steele, and he pulls the hardest. That would be like oxygen. And then say over here we've got a chlorine, and over here we've got a chlorine. So say the juniors and the seniors pull with the same strength. So the idea is this. When we set this up, if these are the juniors, if these are the seniors, if this is the faculty, and we've got steel, so we pull harder, who's going to win? Well, we are, right? The faculty is going to win. But guys, what if we reset the stage and we allowed the juniors and the seniors to pull in the same direction? Now who's going to win? Do you get the idea? So Sam, that's why. The reason that oxygen wins, even though we have 2 chlorines pulling in the other directions, is because their forces are not together, and as a result, the oxygen does outpower the other 2 because they're not working together. Does that make sense? Correct. Well, and not only are there separate things that are not pulling in the same exact direction. And as a result, their pulls don't add up to overcome the pull of the oxygen. And again, guys, I think we talked about this. If you've taken physics, these are called vector sums. So if you understand vector sums, that's exactly what we're talking about here. So, good question. You guys okay to move forward? Okay. All right, so guys, it goes like this then. Isn't it fun to think we might have Spirit Bowl? I like that. No promises. All right. So guys, the idea then is this. When these molecules get together, they attract each other, right? And these attractions are called intermolecular forces. What's going on is the positive dipole of one molecule is attracting the negative dipole of another, and so on and so on and so on and so on. And eventually we get all these attractions working together, and these things stick together in a clump. Well, guys, these attractions are what are called intermolecular forces. You'll notice it's in bold. This is a big, important idea. So, guys, let's break this down. I don't know that you need to do this, but guys, the idea here, we should break the word down. So forces are things that attract stuff together. For example, gravity is a force, electromagnetism is a force. This is a force. It's something that pulls stuff together. So if we look at the word molecular, obviously we know this has to do with molecules like water and things like that. But here's the question. What does inter mean? What does the prefix inter mean? Well, let's do this. And I don't know that you need to write this down. But the opposite of inter is intra. So remember back in the good days when we used to have intramural basketball? Reggie runs it. Kind of. Guys, if you're playing intramural basketball, who are you playing against? Teams from where? Your school. So guys, the idea is that intra means from within. So intramurals means you're playing teams from within your school. Now, if you're on the Orem High School basketball team, that is not an intramural sport, that is an intermural sport. The idea is that you're playing teams from other schools. So guys, the prefix inter means between, playing between schools. So when we talk about intermolecular, we're talking about forces of attraction between molecules. And again, that's the whole idea here with those molecules sticking together. So here's what you need to know about them. These are weak attractions that exist between polar molecules. So then, guys, the question becomes, what does it mean to be weak? And the answer is actually this. IMFs, or intermolecular forces, are somewhere between 1 and 10% the strength of a covalent bond. So they're about 1/10 to 100th the strength of a covalent bond. So then, guys, the question becomes this. Which one is it? Is it 1/10 the strength of a covalent bond, or is it 100th the strength of a covalent bond? And the answer is, it depends. Depends on what? Well, guys, it depends upon polarity. The more polar a molecule is, and remember this was our goal for the day, the more polar a molecule is, the stronger its intermolecular forces will be. And that's what we're going to do to wrap up the day. Guys, we've got about 7 minutes left and we're done. So in order to set the stage then for what we're going to do next time, we've got to be able to figure out how do we know which molecules are more polar. That's the last thing we're going to do today. We're going to draw 3 Lewis dot structures. We're going to kind of do to them what we did in homework last time, and then we're done. But guys, before we do that, there's one more thing that I need to get in front of you in preparation for next time, and it's this idea. Guys, when we talk about these intermolecular forces, we're going to talk a lot about cause and effect relationships. This is true, so this is true, so this is true. Now guys, when we talk about cause and effect relationships, we end up using a lot the word therefore. If you want to see a masterful use of the word therefore, read the book of Romans. It's really interesting. Guys, so many chapters in the book of Romans, Paul begins with the word therefore. And I remember I had a teacher once that told me anytime you read the word therefore, you need to ask what the therefore is there for. I know that's cute, right? But the idea is when you start a paragraph with the word therefore, it means, hey, I just told you that something is true, and that means this is going to be true. It's the way that we develop arguments like Paul's doing throughout the book of Romans. So guys, we are also going to be creating arguments. This is true, so this is true, so this is true. But guys, frankly, the word therefore is a pain in the butt to write a lot, so we're going to do this. Do you guys know about the triple dots? Let me move them down a little bit so it stands out a little better. They sort of creeped in the slide. Guys, if you don't know about this, this is a magic thing. Guys, this is actually the mathematical symbol for the word therefore. So when you're writing out these arguments in your homework on tests and things like that, you can use the word therefore, but represent it by 3 dots. Therefore, it just stands in for the word therefore. And we'll be doing that more throughout the unit. I think you'll even see it in the homework today. Do you guys know that therefore had a mathematical symbol? You're learning so much. All right, so guys, here's the scoop. You're now done taking notes. All we need to do is draw 3 Lewis dot structures. It's going to be exactly like the homework that we just turned in. Nothing new. We're going to draw 3 Lewis, well, actually a little bit new, but we're going to draw 3 Lewis dot structures. And then when we get together on Monday, guess where we're going to start? With those 3 Lewis dot structures. So guys, please in your notes, spreading these out the width of your page, draw the Lewis dot structures for these 4 molecules. 3, I can't count the 3. These 3 molecules. Make them big, literally spread them out across your page, make them big. But then guys, you may end up needing to do some erasing, because remember, we draw Lewis dot structures as 3-dimensionally accurately as we can. Once we're done with these, well, and let's just do it now, draw in the polarity arrows. If you're stuck, don't do them, well, do your best, but also be prepared perhaps to erase. And then guys, when we're done with this, you'll have time to work on your homework. While you're doing this, guys, let me remind you, because we're doing homework online still, set a reminder. Hey Siri, remind me when I get home to record my homework. You guys know you can do that with your phones, right? It's called geofencing. If you set your address in your phone and then you say, remind me when I get home, your phone tracks you, and when you get home, it's called geofencing. It's a mystical, magical, and sometimes disturbing thing. Because as you're drawing these, I know that we got Atticus and I know we got Alex. Does anybody else who wasn't here last time need a copy of the homework packet? You guys are all okay. And you know that if you ever lose these, the extra copies are up there above Josh. So again, guys, we're drawing Lewis dot structures. We're drawing in polarity arrows. Oh, that didn't break. It's a Christmas miracle. Well, see? You can, yeah. On this guy, it does. So here's what you're going to see. We're going to go carbon bonded to 3 hydrogens. Then the carbon is bonded to this oxygen, which is then bonded to the hydrogen. Yeah, not at all. Not at all. Because remember, these aren't 3-dimensionally correct anyway. But what we do want to do is draw it, well, I should be careful. The Lewis dot structure, technically it doesn't matter, but when we draw it as accurately as possible, it will matter. Exactly, because it's bent. Because there's 4 domains and 2 are bonding, it's bent. Yep. Hey guys, if we get deep into this and I forget to mention it to you, there's two things we need to talk about before we wrap up today. The first is what part of your homework you actually need to do, because we're not going to do all of it. The other thing is one more thing about registering for classes. So please, if I forget either of those, don't let me forget. So guys, can we fiddle with these? Are you at that place? Okay, so guys, do this. If you are not arriving at the same drawings that we are, please edit your drawings, because you want to start with an accurate set of Lewis dot structures. Because again, this is exactly where we're going to pick up next time. So guys, let's do CH4 first. I suspect that many of you came up with this Lewis dot structure. Guys, again, is this symmetrical? Oh yeah, so is it polar? It is not polar. So what we're going to do is we're simply going to label it non-polar. Well, actually, we'll do that in a minute. But guys, understand that this guy will not be polar because it's symmetrical. So now let's do this. Let's jump over to water. We'll do the middle one first, or we'll do it last. Let's hop over to water. We've done water before. We know that it looks like this. And again, guys, remember, we're going to draw these best. And so water is not linear. We're not going to draw it like this. We're going to draw it like bent, because in fact the molecule is bent. So we'll represent it like this. Now guys, you may have noticed that the one in the middle, and this is why I'm doing it last, is actually a bringing together of these two molecules. We've got the CH3 from here, and then we've got the OH from here. And so you're literally bringing those two things together to make this molecule in the middle, and it actually looks like this. Now guys, let me just point this out to you. The thing that you don't want to do is you don't want to put your O and then your H there, because that makes it look linear. If you draw it like this, it makes it look linear. So you could go up or down. Just please don't draw it straight across, as you pointed out, McKay, because we need to represent that oxygen is bent, and the molecule actually looks, oh, I'm drawing dots. The molecule actually looks like this, and this is the guy. So guys, doctor up your Lewis dot structures, make sure that they're right. Then all we're going to do is draw in the polarity arrows, and then we're done for the day. Well, and then one other little thought. And then the two things that I need to tell you about. You guys good? You all caught up? Okay. So guys, now let's draw in the Lewis, or draw in the polarity arrows. We've already decided that CH4 is not polar, right? We don't even need to look up the electronegativities. We know that that's symmetrical and therefore non-polar. So guys, what about the other two? Symmetrical? No, not even close. Guys, those are definitely not symmetrical, and therefore they're polar. But guys, in order to then draw the polarity arrows, what do we need to know? The electronegativities. And I actually looked them all up. So you don't even need to write them in, but what I am going to encourage you to do is to draw your polarity arrows so that you can track them. So guys, let's start over here on the right as we did before with water. So oxygen is stronger than hydrogen, so this one's going this way. Oxygen is stronger than hydrogen, so that one's going that way. So what then is the overall polarity arrow? Up and right. So guys, it's this dude right there. Questions if you need. Y'all okay? Okay, now guys, this last one we saved for last because it's a little weird. So let's track all the arrows. So drawing in the polarity arrows, hydrogen's 2.2, carbon's 2.55. So all of these, I believe, go towards the carbon like so. Then oxygen is 3.4, carbon's 2.5. So this one goes towards the oxygen. And then the oxygen-hydrogen bond also goes towards the oxygen. Were any of you brave enough to try to draw in the overall polarity? Okay, yeah, that's exactly it. So, guys, how does this go? Well, all of these are closing in on the carbon and then moving towards the oxygen, but then this is coming up. So all of this actually flows up and right, and that would be the polarity of this molecule. Go ahead. Yep. No, it would still go this way. Well, hold on a second. Wait, stop. No, hold on. So if it was like this and that wasn't there, it would go this way. Yes, no, I'm wrong. Ooh, that was bad. No, it would go that way. You guys okay? So now the last thing that you need to be able to do, and then we're really done, guys. The last thing that we need to do is put these in order by polarity. Which one is the least polar, which one is middle polarity, and which one is the most polar. Now, why do we care? We care because of the therefores. Because the one that's the least polar will have the weakest intermolecular forces. The one with the highest polarity will have the strongest intermolecular forces. And that's where we're going next time. So, guys, which one of these is least polar? That guy. No, you can't be less than not. So, guys, the least polar is CH4. So, guys, let's do this in our heads. You ready? If a molecule is not polar, therefore, if a molecule is not polar, therefore it won't have intermolecular forces. Therefore, the molecules don't stick together. Therefore, the molecule will be a gas. And guys, what I'd like to do is I'd actually like to show you a big old sample of CH4 molecules. You ready? Hold on, let me get them for you. You ready? So guys, big sample of CH4 molecules coming at you. Guys, CH4, this stuff, is actually Bunsen burner gas. And the reason that it is a gas is because these molecules are not polar, therefore they don't stick together, they don't have IMFs, and they spread out in the room as a gas. We'll talk more next week, okay? So now let's figure these two dudes out. And guys, here we've got sort of an interesting thing going on. Both of these are polar, but which one is more polar? Or more importantly, how do you know? And guys, here's how to know. The polarity of the molecule is determined by the polarity of the bonds. Now remember the question I screwed up in the homework? That homework question was bringing you to figure out the polarities of bonds. And the way to do that is by subtracting. So we are going to figure out the polarities of these bonds. But guys, here's the thing that's nice. We only need to figure out the polarities of the bonds that are sitting right next to the arrow. So all we've got to do is a little bit of math to figure out the polarities of these bonds. And guys, it goes like this. 3.44 minus 2.2 is 1.24. Do this with me. So that's the polarity of that bond. Then guys, here, carbon's 2.55, so 4.5. All right, I'm embarrassed to say, to do that subtraction, I'm going to use my calculator. So 3.44 minus 2.55, that would be 0.89. So guys, the polarity of this bond is 0.89, the polarity of that bond is 1.24. The electronegativities. So, London, here, let me do this. Let me clean up my mess. So what I did is I took 3.44 minus 2.20, and then I took the polarity of the electronegativity of carbon, 2.55, and went 3.44 minus 2.55 to get that one. So just subtract their electronegativities. Okay, so that brings us to there. Now guys, let's do the same thing for water. So 3.44 minus 2.20, this is 1.24, this is 1.24. And again, guys, we're only doing this for the bonds next to the arrow. So now, which one is the most polar? And the answer is the molecule with the most polar bonds will be the more polar molecule. So this one is made by bonds with polarities of 1.24 and 1.24. This is 1.24 and 0.89. So which one's more polar? The water. Water is more polar because its bonds are more polar, and then CH3OH is in the middle. The bigger difference. Yep. The bigger difference will be the more polar molecule. Are you guys good? Are we all done? Okay. So guys, grab your homework packets. Turn to page 2. And you'll notice that it says 2 and 3. You know what? I'm realizing it might be easier if I just do this in front of you. So let me pull this up. So general chemistry. This is actually what the back side of our website looks like. No, not that. Okay. So guys, this is the first page of this homework assignment. And here's the way this is going to go. Please don't write this down, but let me just show you. So we've got the therefores. So polarity, therefore IMFs, therefore boiling point. Now guys, here's the trick. You will only be looking at the left 2 columns. So if there is no information in the left 2 columns, you will skip it. So you will not do number 1, but just do this with me. Let's look at number 2. Guys, in number 2, if we have a polarity that is low, the down arrow just means low. If we have a polarity that is low, that means the intermolecular forces will be low. Low polarity, weak IMFs. Now guys, this one we can't do because we don't have any information. Now number 3. Guys, what does it mean if the intermolecular forces are strong? That means the polarity is strong. High. But you can only do these for the ones where you have information in the left 2 columns. Skip the rest, we'll do them next time. Oh, sure. Yeah, they're always the same. Yeah. You're looking for trends. Are you guys already done with the first page? Yeah, right? Hey, you learned something. I know, right? Then, guys, this. Page number 2. Yeah, guys, page number 2, you're going to do all of these. Page number 2 is basically what we did on the last thing in class. Draw their Lewis dot structures. So, like, for example, you would draw CH3 or CHCl3 here, CHBr3 here, then draw in the polarity arrows, and then indicate which one is more polar. You'll do that the whole way down. Now, guys, with that said, when you get down to the last 2, 5 and 6, please plagiarize the Lewis dot structures. You do not need to be able, well, that's not, I should take that. This one you should be able to do largely because we just did it in class. Plagiarize this one, and plagiarize that one. Those are not Lewis dot structures you need to be able to come up with on your own. But once you've got the Lewis dot structures, you should be able to draw in the polarity arrows, and you should be able to figure out which one's more polar. Sam, go ahead.
So you mean by plagiarize,
Copy them from the answers. Yep. And then, guys, you're done. You'll notice that there is a 3rd page to this assignment. Don't touch it. We're going to do that next time. Okay, so guys, with that said, allow me to offer one more thought relative to registration. And I need to be very, very careful about how I say this, but it would also be wrong of me not to mention this. And please understand, this is being recorded. Please understand that this is not me speaking ill of anybody else's classes or programs here at this school. But let me say this, or our counselors. Guys, when you go to talk to your counselors about forming your schedule for next year, you need to understand that your goals and the goals of your counselor may not be the same. Our counselor's primary objective is to get you to graduate. They care about credits. They want you to get credits. Now, guys, understand there's lots of ways to get credits, but many times the way that you get credit is not in your best interest. So, guys, I'll say this. When you're thinking about the science classes that you're thinking about taking for next year, you need to take a deep, long look at what your goals are down the road. Because there are ways that you can get credit that will get you to graduate that are not best for you relative to where you want to be in a couple years. I will be open and honest with you if you'd like to talk about these things. But guys, increasingly, we have students that come back to us their senior year and say, I wish I had. Guys, please do not put yourself in that position. I'll leave it at that. Guys, the rest of the time is yours. You're all done with this already, right? You just need to do the next page. Don't forget to record your homework assignments tonight. And guys, we'll see you on Monday. But we do still have 15 minutes. Look at